So, as Eric advertised it, we're gonna dive deeper in word representations, but unfortunately, we're gonna stay pretty shallow actually. So today, I'm gonna talk to you about fastText, which is a library for efficient text classification and word representation learning. So I'm Piotr Bojanowski. I'm a postdoc at Facebook AI Research right now. So anything I'm gonna talk to you about today is joint work with some collaborators at some of my colleagues at Facebook, Edouard Grave, Armand Joulin, and Tomasz Mikolov. So just to give you some context, some scientific context around that, well, I mean, I don't need to convince anyone that actually like representing words as vectors is interesting. I mean, everyone has used word vectors for some applications, and the implementation of word2vec has seen a huge success. But there are some drawbacks to word2vec. One of them is that you cannot like build easily sentence representations with word2vec. I mean, people take like average vector over a sentence and use that, but well, it doesn't work actually that well. The other thing is that it doesn't exploit morphology in any way. So words that have the same radicals are going to be like represented with different parameters. So disastrous is going to be represented differently from disaster. However, the implementation of word2vec was very efficient, very fast, and very simple to use. So it was very widely used. Okay. So the goal of fastText was to build a unifying framework in the context of two papers that we did. One was about text representation learning, the other one about text classification, where the core of the library would be that given a set of indices in some dictionary, you want to predict an index in another dictionary. So actually cbow in word2vec, skipgram, and text classification are actually can be seen as instances of this model. Like in cbow, you have many words, you predict a word. In skipgram, given a word, you predict a word. In text classification, given many words, you predict a label. Okay. So there are going to be two main applications. The first one is text classification, in the sense that given a big block of text with a paragraph, maybe more than just a sentence, we want to predict that, for example, this one is about written work. The second application is going to be about training word representations that are going to have character level features in them, okay? So, for example, for the word mangerait, we're going to extract character level, character n-grams, sum the character n-grams, and use them to predict the surrounding context. So I'm going to start quickly with some background about skipgram and cbow, so that everyone is on the same page about the notation that I'm going to use. So there were these two models in word2vec. cbow is like given a context, you sum the vectors and you predict the word in the middle. Skipgram, on the other hand, given a word in the middle, you're gonna like successively predict all the words around, okay? I'm gonna start with some details about the skipgram model, where in this sentence, for the example night, you want the feature of night to be very discriminative to predict Lancelot fought bravely mighty, okay? So what you want to do is to model the probability of context words given a word. So you have features for the word W, XW. You have some classifier for the context word C, VC. And you want to maximize the probability of the context given the word, which you express as as a softmax like this. The word vector that you're going to use in the end to do your nearest neighbor queries or use them for some downstream task is going to be the XW here. So you train this model by doing like a minimization of a negative log likelihood. So you have a stream of word in a big corpus, like let's say Wikipedia, and you minimize with respect to X and V the sum over this data set of this probability, negative log likelihood of the previous model. So this thing actually hides the co-occurrence counts that are classically used in training word representations. Instead of summing over the dataset, you can sum over the dictionary by just weighting your examples. So the main bottleneck of this kind of models is the denominator of the softmax, which is very computationally intensive. So I'm just going to very quickly go over the two approximations. You usually replace like the multi-class loss by a set of binary losses, either by doing negative sampling. So you have the positive word in the context, and then you just sample some random ones in the dictionary. Otherwise, you have the hierarchical softmax, where you represent every word as a set of codes. These codes are obtained by computing the Huffman tree. In the end, very frequent words are going to have short short codes, sorry, and very infrequent words are going to have long codes. So it's very fast to evaluate, and you just sum over the codes for every example. So now, just quickly, the cbow model. cbow is the other way around. You're given a context, and you want to predict the word in the middle. So we want to model the probability of a word given a context. So you have a feature for the context, HC, so I don't call it X, I call it H. You have a classifier for word W, VW, and then you model the probability of the word given the context exactly as before. But what is HC? It's just the sum of the words in the context, and that's why it's called a continuous bag of words, because instead of just like doing a sum of indicators, you do a sum of dense vectors. So fastText is something which encompasses a broader set of models, where basically the only different thing is the pooling strategy. So what are the inputs and what are the outputs and in what dictionaries? So it's an efficient and modular C++ implementation. And it's easy to use it's easy to write extensions by just changing the pooling strategies. So I'm gonna talk about the first application, which is like bag of tricks for efficient classification. So given like this block of text, you want to say that it's an artist. Given this text, you want to say that it's about a natural place. fastText in this context is a very strong and very fast baseline. So if you want to train a classifier for text very quickly and have decent results, fastText is exactly meant for that. The ease of use is at the core of the library, because you just like download the code, do make, and then fastText supervised the input data, the output where you want to save your model, and you can train. So that trains, and this is for testing. This time you want to model the probability of a label given a paragraph. So you have a feature for a paragraph, which is going to be HP. You have a label L and a classifier VL. So you model exactly as before, P of L given P, where the paragraph feature is the sum of the word representations inside. So the word vectors XW this time, we're going to optimize over them, but they are not actually useful. We didn't evaluate them. We didn't use them for any task. If that data is scarce, so you cannot train well your model, you can bootstrap it by just preloading some word vectors that you trained on Wikipedia without labels. Words are maybe not enough for classification, so you can actually use higher order features by, for example, for this sentence, using not only the unigrams, but also using 2 grams, or going to higher orders. But you want to avoid building an n-gram dictionary, because like if you have a 1 gram dictionary of size k, if all 2 grams appear in the training set, you would need to build a k-squared dictionary, which can grow very quickly. Instead of doing that, we propose to not actually build a dictionary of n-grams, and we use a hashing strategy to compress it to b buckets, which you can just like adjust so that your memory doesn't overflow. So we evaluated this fastText implementation of the kind of cbow for classification on sentiment analysis, and compared to like some of the state-of-the-art approaches, which are using like deep convolutional neural nets on a character level. Yeah, they are all on character level actually. The interesting thing is that if we use bigrams and a hidden of 10 dimensions, we actually get performance which is on par with the state-of-the-art. The most important part of it is that we don't need like 5 days to train it. we train it in 10 seconds. So you do lose some of the critical accuracies in some applications, but you do it in 10 seconds, okay? The second thing on which we evaluated is tag prediction, where given Flickr data, given an image caption, you want to predict the tag. So these are like examples from the data set. Again, we compare to tag space, and you see that we get like better accuracy in training, like in 13 minutes instead of 5 hours. Okay, I'm gonna jump now to the second application, which uses the same model and the same core of the library, but does something different, okay? It's about enriching word vectors with subword information. We want to represent words by this as the sum of the character n-grams. We add special like positional characters so that, for example, mangerait is gonna have like a beginning of word character and end of word character. And we want this invariance to enforce that grammatical variations are gonna have roughly the same mixture of n-grams. So I'm Polish, and there is declension in Polish. So there are 7 cases plus like singular plural. For university, you just get like 14 different versions of the same word, which has the same radical. And you don't want to represent these 14 different words as 14 entries in your dictionary. The second thing is that compound nouns are now easy to model. So if you have like Tisch, which is table in German, tennis is tennis, Tischtennis is like table tennis. And you want to represent it as the sum of the n-grams that constitute the words. So the model is roughly like skipgram. We want to model the probability of a context word given a word. We have a classifier for the context. We have a feature for the word, now H, not X. As usual, the softmax. And the feature for the word is computed using n-grams. So we take all the character n-grams, but we actually also use the word itself. Okay. As for the previous classification model, we don't want to store all the character n-grams that you see on the dataset. For Finnish or Turkish, it would totally go crazy. So you do hashing on this dictionary. One of the big advantages is that it's possible to build vectors for unseen words. Imagine you have a word that you haven't never seen. So this part is not in the dictionary. You don't have any parameters for that, but you still have something for that. We're gonna evaluate it in the experiments and compare, like, if I don't have a word on a test set, either I can just output a vector of zeros and consider that my similarity with every word is 0, or I can do the sum of n-grams. So the first task on which we evaluated our word embeddings is the word similarity. So you have like pairs of words, a human judgment of similarity. We compute our similarity as the cosine similarity between the two vectors, and use the Spearman's rank correlation between the two lists of doubles. So we evaluated on Arabic, German, English, Spanish, French, Romanian, and Russian. These are the languages for which we have found word similarity datasets. Ours with a star is the one where we don't compute vectors for words which are outside of the vocabulary. So we just put zeros for the words that we don't know. And ours without the star is the one where we actually build something up from n-grams that we have. All this was trained on the full Wikipedia dump we have found. And what we see is that, well, ours outperforms the word-to-vec baseline on all languages and all datasets except word similarity on English. What's interesting is that it works basically well for datasets where you have rare words or languages which are morphologically rich. You see that on German, you have like a big boost of improvement, a boost of performance. And on rare words, which is a dataset specifically tailored for like infrequent words. Russian also works quite well. Declensions are in Russian, so that might be a reason. The second evaluation is word analogies, where given like a tuple Paris, France, you're given Warsaw, you're supposed to predict Poland. You can evaluate it using accuracy. So basically count the number of such examples where you get it correct. We evaluated on Czech, German, English, and Italian with the word2vec, skipgram, and cbow, and our model. The interesting observation is that it actually, our embeddings work very well for syntactic analogies, and especially for languages where there is declension, like, German and Czech. Well, you lose just a bit on the semantic analogies for all languages, but not that much. So we compared to state-of-the-art methods. I won't go into details, but they need to be trained like all of the morphologically rich representations in the literature. Like, they trained their models on very specific data sets. So for groups of methods, we had to actually train our models on the same data sets in order to make everything comparable. And we get performance which is better usually than the state-of-the-art. Just some qualitative results, like doing nearest neighbor queries. For example, English born, in our case, is gonna give like British born and Polish born, because you actually share a lot of n-grams at the end with these words. Whereas skipgram won't find anything meaningful in that case. The other interesting example is, for example, eateries, where both methods is gonna find restaurants because it's almost a synonym. But in our case, we also have like the features from the n-grams which pop up and make these like words which have singular versions of the plurals which come up. So I'm ready to take some to conclude. So fastText is open source. It's available on GitHub. After 4 months, it has already like 5,500 stars. There is a large and active Facebook group with users who post like their problems with training the model, other kind of stuff. It was featured in like popular tech press. It's C++ code with absolutely no dependencies. So you can, if you have a modern, like a modern architecture, like C++ 11 enabled, you can compile it with just make. So there are some bash scripts available for the two applications I described, so you can try it out. It's very simple to use. There are some open source projects around, like a Python wrapper and a Docker file integration, so that you can ship it like in production if you need it. With that, I am ready to take your questions. Yeah. Where's the box? I'm very bad at throwing, so. See, told you.
Thank you. Okay, thank you very much. Just a question that has nothing to do with the a question that has nothing to do with the algorithm. Did you try to parallelize it?
So it is multi-CPU. It's parallelized with like Hogweld, so you can like as word2vec.
Yeah, but
you basically use it on 40 CPUs if you have a big data set. We didn't work on multi-machine.
Multi-tenant?
No.
Okay.
Like on most data sets on which we trained our models, and with the hashing trick, if like you have a machine which is modern in the sense that it has like 10, 20 CPUs plus a lot of RAM, you can take most of the data sets. Either way, like one of the main bottlenecks is going to be the construction of the dictionary and the fact that you need to do 2 passes on most of the like huge data sets. So the code is not available for that, and it's something we want to work on in the future to make it like totally just doing 1 pass over the data and never seeing it again. But for now, you don't have the problems of parallelization over multiple machines with the datasets we trained on.
One other question that has to do with the mathematic model.
Yeah.
You implemented everything with empirical averages, I guess, or
Yes.
you just summed the count of words?
Yes.
Did you try to sum the count of word by frequency in the corpus of document?
No. So we just do like stochastic gradient descent. So we pass through the data exactly as word2vec does.
Okay. And what about the temperature parameter in the softmax? Is it always the same, or did you have also...
It's a decreasing learning rate.
Okay.
linearly decreasing. I think some
also
people
gradient
tried with
descent?
different decay steps. Okay, step size or learning rate, depending on if you're deep or shallow. Some there might be some gain. We found that linear decrease was fine.
Thank you very much.
Nice shot.
So I have a question about, like, if you have a cross-lingual, so you have a multiple language, French, English, and you want to keep the context of the different word in those different languages. So can you do this with fastText? So basically, what I already did it with word2vec.
Yes.
So you have like one word in specific language, you get the context of this word in another language.
Okay.
So can you
Given
do
like
this
a parallel corpora or something like this?
Yeah, with parallel, with aligned text.
So we have not done anything like that, but that's why fastText is good for you, because it's like kind of modular in the sense that you can write basically your data loaders, some in C++, provide like 2 dictionaries in 2 languages, and just feed it to the core of the library, which is gonna do like the stochastic gradient descent on the parameters. It's just a different way of pooling, in my opinion.
I use like the skipgram model, so I took
You
one
modified
line.
the C code of Tomasz?
Sorry?
Did you modify the C code of Tomasz?
No, I didn't use fastText. I use word2vec, but
yeah, but word2vec is like the C code, right?
I use like the Python
the
and
Python version, okay.
Cython
The
implementation.
Gensim, yeah.
And so I wanted to know, like, if you can do this also easily through fastText. So like using a skipgram model, but on a line text.
If you modify the at the right place, of course.
Okay.
It's supposed to be written in C++ so that it's fairly easy to read and modify.
Okay, thank you.
So maybe just one thing to say. One interesting thing was to actually train it on multiple languages, mixed languages, because like you will have some similarities across languages. For example, Czech and Slovak. So you can like actually mix the 2 Wikipedias and see if that gives something. Or for example, all Roman languages, all Slavic languages, and see if you come up with something. I think the problem is that in our case, the classifier is just the word. We don't use the n-grams here. So that might be a problem.
Okay, thank you.
Can you talk about the word database, data set, word dictionary?
Say it again.
Can you talk about the word dictionary?
Yes.
The data sets that you're using as input, how rich are they? How are they collected?
If we are talking about the word morphologically rich word representation learning, we always trained our models on the Wikipedia dump that was available in August. So English is like more than 2.5 billion or 3 billion words, I would say. And then it goes like decreasing quite quickly for other languages. We have seen that it's very important to have a very big data set for models like word2vec, because these are gonna like pick up subtleties only when the data set is big, because of the zip flow that Eric talked about. Since our model uses some like redundancy in a lower level, you can actually build quite decent models with lower, smaller data sets. Yeah, I don't know if that answers your question. Or...
I'll ask you afterwards.
Okay, sure.
Okay, what I wanted to ask is, from an applied point of view, the advantages of word2vec and distributional semantics is that you can leverage the fact that there exists like, well, it's unsupervised, so you have like volumes of data that you can use them to learn about semantics. But in the example you showed of text classification, that would mean a load of annotated data.
Sure.
So if I understand correctly, you preload word embeddings.
You don't need to.
You don't need to.
No.
So
that's why
if I have a tiny,
it was 10-dimensional, because the data sets are too small to build a rich representation.
But it's still performant, let's
Yes.
say. Yeah, okay.
You can
Interesting.
bootstrap it with something that you pre-train on a huge data set.
Okay.
And it, for very small data set, is actually the key to having a good performance.
Okay.
Most of the issues we had on GitHub or people reporting bad performance was because they were training on like 1,200 examples. And
If
it's definitely
labeled,
not,
yeah.
it's not meant for that. So what you say is true, but for example, Flickr with tags and captions is huge.
Yeah.
So there is data, which is not like fully supervised in the sense that no expert went and labeled the thing.
Yeah, but you could pick your data set. This is not the case in general. General, the data set comes with what you're
Yes, I know.
doing.
Of
Okay.
course. So you can bootstrap with unsupervised word representations, and then the classification performance should be good.
Thank you.
You can use fastText to train the words.
I'll
the
give it a try.
representations.
Peut-être on peut juste le
Multi-hop.
forwarder. Hein?
Okay. There was a droit de douane.
I want to ask if it's possible to, since with Word2Vec, it's we can only build the vocabulary list for one time. So if we do the online training, we cannot add the new words into our vocabulary list. So I'm wondering, with your algorithm, will it be possible to update the vocabulary list?
Not right now. So that's something we wanted to work on. What, if I understand correctly, what you are saying is that you would like to actually build a dictionary and learn the model at the same time.
Yes.
In a setup, for example, where you see your data only once. It comes as a stream, and you cannot save it. So no. The simple solution would be to get rid of a dictionary and hash everything. Whatever comes in is just a hash in a bucket. There's gonna be like collisions in your hashes, but well, that's life. It should work pretty well, I guess.
So thank you, Piotr. It was very interesting. I played a bit with fastText and
hard questions now, right?
Yeah, technical. No, actually, so what I did was I take the vector representation of a word that was in the data, and I
sorry, in the supervised classification setup or the
no, just I did unsupervised learning of word vectors, and so I took a word vector that were learned during the data, and I constructed, built another word vector made up only with the n-gram vectors. So without this special vector for the word, and I found out that it was very similar. The two vectors were very similar in general, like the cosine similarity were like 95% or something like that in average. And so I thought, why do we need a special vector? Maybe it would work without. Have you tried?
We have not.
Without the special vector?
We have not. I guess it would work. I don't have a good answer for that. I guess there are examples of words which are made up of character n-grams, which are very frequent and not discriminative. And for these words, you don't want to have just the character n-grams. An example would be, I guess, the stop words might be an example. So probably what you could do is just shrink the dictionary to the strict minimum, because actually, as you say, it doesn't play an important role for most of them. So that might be a solution.
Okay, thank you.
To shrink it out to the minimum. Any other questions? Yeah, last one.
Okay, I have seen that for your representation with morphology, for French, you have no gain.
No.
And well, I know that French is not a very rich morphologically language, but still we have some morphology more than English in a way. And for English, you have 1 point gain, I think. So do you have some explanation for that? Because I also think that for French, your data set is smaller than for English. So adding more in a way, more feature should improve.
I object to your remark. There is a boost, but which
no,
is not
but for the other ones, but between our stars and
yeah,
ours.
okay. So basically, the fact is that if all the words were seen in the training set, you don't have a difference between these two.
Okay, so for French, there is no unknown word.
So there was a column in the paper. We removed it, I think. There was a column of like out of vocabulary word frequency. I think for French it was 0. Okay. If you try on whole Wikipedia and check if the words in RG65 are in the whole Wikipedia, I think they are.
Okay.
They are not for this one. For Arabic, I think they were not.
Okay.
Okay, last one.
Thank you, Piotr. My question was, do you think that instead of getting the character anagrams, we split the words like with a set of rules, like we stem them and get with the prefixes, the suffixes? Do you think it would work better because we inject a little bit more knowledge into the system?
So two things. First is that anything you do of this kind is going to slow down the training, because now you have like a pre-processing step, which is probably going to be like quite heavy actually. And we were like actually trying to make it as quick as fast as possible. So that's on the algorithmic part. But on the other hand, if your parser is perfect, maybe. Otherwise, you might be learning a bias. So here, the norms of the vectors are not fixed. So if there is something which is not useful, we didn't do any like qualitative evaluation of the norms, for example, of the character n-grams. Might be actually that if you train on a data set which is large enough, you come up with the norms being correlated with the actual part, like some interesting decomposition of the word in the morphemes. I'm not sure about that. It's
but that's actually something that we can test with fastText because it's modular and
yes.
stuff. Okay, thank you.
Okay. Thanks.